Hey everyone, welcome back to the channel. In this video, I'm going to go over Ethernet standards, cable categories, cable types, and pin positions. Ethernet refers to an entire family of standards, and those standards define the rules that a node must follow to be part of the network. Ethernet also supports a variety of options for the physical connections, but the most common that you'll see are copper and fiber. Now, Ethernet also supports a variety of different speeds. You can have speeds ranging from 10 megabits per second to over 100 gigabits per second. In terms of copper and fiber, the fundamental difference is how the data is transmitted. With copper based medium, the data is sent by changing the voltage on the wire to communicate ones and zeros. Whereas with fiber, the light is modulated to communicate those ones and zeros. Additionally, there is a cost component to consider when choosing between copper and fiber. Fiber typically is more expensive. However, it does allow you to communicate over a longer distance. Here are some of the standards from the IEEE for Ethernet, and we're going to use them to get an idea of how they're named and also compare them in terms of the speed and distance that they cover. You may have heard of terms such as fast Ethernet, Gigabit Ethernet, maybe even some of the formal names such as 100 base T. So, what does that all mean? In terms of the formal standard from the IEEE, the numerical value identifies the speed of the technology in megabits per second. So, for example, at the top we have 10 base T. That is a 10 megabit per second formal standard. Now, base indicates that Ethernet is a baseband technology. And you don't need to really know this for the CCNA, but just to give some context, it's just referring to the fact that the transmitting device has full use of all the bandwidth on the cable because Ethernet does not have a concept of sharing a wire with multiple devices at the same time. Now, the last part of the formal standard can either be a letter or a number. Numbers indicate the max length of the cable in meters. So, for example, if you had a standard that said 10 base 5, that would mean that it is a 10 megabit standard at the max distance of 500 meters. However, there could also be letters, and if you see letters, that indicates the cable type. If you see a T, that's typically for twisted pair, and if you see an X, that typically indicates fiber. One of the strengths of Ethernet is that it behaves the same across different physical link types. So while Ethernet itself covers different physical layer standards, it's consistent in the way that it's applied across those standards as the same data link layer rules apply. So, regardless of the physical media that's used or the speed of that media, the same format is used at the data link layer to send a frame on the wire. So, if we have a computer here, computer A and computer B, and let's say that we have some data and we want to send that data from computer A over to computer B. Get our Ethernet header and trailer here. So if we take a look at the pathway that this frame is going to traverse, the initial link between host A and the switch is 100 megabits per second unshielded twisted pair link. And we'll get into what unshielded twisted pair means in a moment. And that link is 80 meters long to the switch. Now, if we take a look at the next hop, we're going to see that this link between the switch and the router is a 1 gigabit speed fiber connection. So the speed and the media type has changed. And additionally, this is a longer distance. This is 300 meters. And again, fiber can travel over longer distances than copper. That's one of the benefits to it. And then we can see the same thing here between the routers. So this is a 10 gigabit per second fiber connection. And this is 1 kilometer between the routers. So again, the speed and the distance is changing, although the medium has stayed the same in this instance. However, we can see here that it's changed. It's gone to a 1 gigabit per second speed shielded twister pair cable, which is 80 meters long going down to the local switch. And then finally, we get down to the communication pathway between host B and the local switch, where again, it's just a 100 megabit per second connection and it's 50 meters away. So while this communication has happened between all these different hops, by the time that this frame gets over here, it is in the same exact format. So the same rules apply regardless of the medium that's used along the way. So before we said that Ethernet sends data using electricity that flows over the wires inside of a cable. Now, if you take an Ethernet cable and you open it up and look inside, you'll see 8 copper wires that are paired together and they're twisted. And this twisting helps solve some important physical transmission issues. When electrical current passes over a wire, it creates electromagnetic interference, and that can cause issues with electrical signals in nearby wires, including wires that are even on the same cable. So, twisting the wire pairs together helps cancel out most of that interference, and as a result, most networking physical links that use copper use twisted pair cabling. And you may hear the term crosstalk. This is where the interference between wire pairs are in the same cable. In this visual here, we have two different types of cables. We have a shielded twisted pair and an unshielded twisted pair. And as the name indicates, for the unshielded twisted pair, there is no further shielding from electromagnetic interference for this cable. However, if you take a look at the shielded twisted pair, you'll notice that the wire pairs are enclosed by an outer shield that helps further reduce electromagnetic interference. Additionally, some cables come with a outer shield that covers all the wires on the cable to further reduce electromagnetic interference. So this is a similar concept to what we see here for the shielded twisted pair, where there's an outer shield that further reduces electromagnetic interference. The difference here is that this outer shield applies to all the wires. So how shielded twisted pair is applied to the individual wire pairs. In this case, with this screening, it covers all the wires that are within the cable. And this can apply for both shielded twisted pair and unshielded twisted pair cables. So it's not exclusive to one or the other. And if we take a look down here at this top level view of shielded twisted pair and screened shielded twisted pair, we'll see that in the shielded twisted pair example here, which is what this cable is, we'll see that we have the outer sheath, which is just a plastic coating. We'll see that right there. And then inside, we have the cables that are individually wrapped inside of that protective shield. And that's it for that type of cable. However, we'll see that for the cables that have the screening, that outer shield, in addition to the individual cable pairs that are protected, there is an additional outer layer that covers all the wires, followed by the outer sheath itself. And as we went over before, the outer shield that covers all the wires inside of the cable to further prevent from EMI, that is not exclusive to one type of cable, either shielded twisted pair or unshielded twisted pair. And we can see that here in this example, we have the cables that are twisted together, and there is no shielded twisted pair inside of this cable where the individual wire pairs have an outer shield. They're just twisted together, just like here. However, we still have that outer shield that covers all the wires to give us a little bit more protection against EMI. All right, let's go ahead and clear the screen and talk about the cables themselves. So inside of an Ethernet cable, we have 8 wires, and each one of those wires has a color associated with it. And then those wires are inserted into an RJ45 connector, and then that connector goes into both ends of the devices that you want to communicate. For example, your computer and a local network switch. And if you take a look at the connector itself, you'll notice that the cables are inserted within a specific order, and they're inserted into a pin. And this pin is used to communicate with the device that you're connecting it to. So you'll see that there are 8 metallic connection points that the cables are inserted to. When it inserts into the RJ45 connector, it goes into a specific pin position, which is referred to as pins for short. And then these pins here make connection with the interface that you connect to either on a switch or a computer, for example. So RJ45 is the common connector of choice when you want to use copper cabling for your Ethernet cable. But what if you want to use something like fiber? We saw previously in this video, we had two routers that were 1 kilometer apart, and for that we had to use fiber. If you don't have a dedicated fiber port on the device itself, you may have an SFP port, which is pictured right here. And an SFP port allows you to accommodate different media types by plugging in a module. So, for example, if this is a switch in this picture, but if it happened to be a router, you can take a SFP like this, which is a fiber SFP, and you can insert that into this module slot, and then you can connect your fiber cable to connect your devices together. Now, that doesn't mean you only have to use fiber. They do make copper SFPs like this guy right here. So you can take that SFP and also insert it into here and then take your RJ45 and connect it. That's perfectly fine to do so. However, this just highlights the flexibility that you get with SFP ports. So let's take a brief look at categories of cables. So cables are tested by standards bodies to see how they perform, and it gives you an idea of how rigorously a cable was tested to meet a certain standard. And typically, this is measured by twist per centimeter and the thickness of the sheath of the cable. So, the more twist per centimeter that you have, the less chance of electromagnetic interference affecting the cable. And then, additionally, the thicker the sheath is also helps prevent EMI from affecting the cable as well. So, generally speaking, the higher the number, the more twists per inch and the thicker the sheath of the cable. And you can kind of see that here in this picture, and it's a little blurry, but if you compare the Cat5 cable at the top versus the Cat6 cable at the bottom, you can see that the Cat5 cable, while there are twisted cables there, they're not twisted to the same degree as the Cat6 cables towards the bottom. You can see the Cat6 cables at the bottom clearly have more twists per centimeter. They're more tightly twisted together, and they should be able to resist electromagnetic interference a lot better than the Cat5 cable at the top. So let's take a look at how a twisted pair cable makes a circuit in order for data to be communicated. So before an Ethernet cable can send any data, first an electrical circuit needs to be created, and that circuit is created by using two wires inside of a single twisted pair. So if we have, for example, a transmitter and a receiver, and we'll call this host A and host B, there is a single wire in each twisted pair that is run between the transmitter and the receiver. And this allows an electrical circuit to be created so that data can be transmitted. So at this point, then node A can use an encoding scheme to transfer data to node B. So node A will transmit that data using electrical signals that vary over time, and then the receiving node, which is node B in this case, will then interpret those changes in the voltage on the wire as either a 1 or a 0. Now let's expand this concept a little bit and take a look at how these two hosts will use the pinouts to communicate the data. So in this case, we have a 100 base T cable, and in that type of cable, there's two pairs of wires in the Ethernet cable that are used. One pair is to transmit and one pair is to receive. So for communication to be successful, the wires in the cable need to align with the correct pins on the RJ45 connector. So for example, we have host A here, and we'll say that host A is a computer, and then host B is a switch that the computer is connecting to. Now the computer network interface card transmits on pins 1 and 2, and we'll put in a receive here, and as well as our secondary circuit, and it receives on pins 3 and 6. Now knowing this, the network switch does the opposite. So the network switch is going to transmit using pins 3 and 6, and it's going to receive using pins 1 and 2. And this ensures that the computer and the switch, when they're trying to communicate, we have the transmit communicating with the receive on the opposite end. That way the communication is successful. Now this is referred to as a straight through cable. And it's called a straight through cable because the pins inside of the cable are in the same placement at both ends. So we have pin 1 at one end of the cable connecting to pin 1 at the other end of the cable. Same thing with pin 2. Pin 2 connects to pin 2, so on and so forth. So all of these wires from end to end are connected in the same position at both ends of the cable. And you can see that in this illustration here. So a straight through cable works well when you have two devices that use opposite pairs for transmitting and receiving data. So if you're connecting a computer to a switch or a switch to a router, a straight through cable is perfectly fine. However, what if you have two devices that are the same that you need to connect together? What if you have two switches that you need to connect together? Well, in that scenario, you need to use a crossover cable. So a crossover cable is used when you need to connect the transmit pins on one device to the receive pins on the other device. So for example, if we had two switches and we want to connect them together, a crossover cable would be used so that the transmit pins at 3 and 6 on the sending device at the other end of the cable are crossed over and connect to the receiving pins, which is 1 and 2, on the receiving switch. And we can see what that looks like here in this illustration of a crossover cable. We have the transmit pins here, that's 1 and 2, and they cross over to 6 and 3. And that's also the same on the opposite side of the cable, where we have the 1 and 2 on this device crossing over to 3 and 6 on the other side. And this is how you would connect two like devices together in order for them to communicate. So for the CCNA exam, you need to know which type of cable needs to be used depending upon the circumstance that you're operating within. And the easiest way to figure that out is to think about it in the layers that the devices operate. So you have a switch, for example, which is a layer 2 device, and you have a router that's a layer 3 device. In that scenario, you need a straight through cable. So a straight through cable is needed whenever you're connecting devices that operate in different layers of the OSI model. However, if you have devices that operate within the same layer of that model, so if you have two routers, for example, or two switches, because those devices operate at the same layer of that model, you would need a crossover cable. Now, most devices today have something called auto MDIX, and that automatically detects the cable type. So even if you use the wrong cable, the network adapter within that equipment can adjust the send and receive pin logic to correct for the error. So most of the time in practice, this is not really an issue, but it is something that you need to be cognizant of, and it's something you will see on the test. Now let's take a brief look at fiber optics. So with fiber, light is passed through a fiberglass core to transmit data. And the light is varied over time to encode zeros and ones. There are three outer layers that are used to protect the inner layer. So we have the outer jacket, the strength member, and the coating, and that all protects the cladding and the core. Now, the cladding and the core work together to create an environment needed for data transmission. There are two types of fiber. There's multi-mode fiber and single-mode fiber. With multi-mode fiber, there is an LED-based transmitter that shines light into the core, and then that light reflects off of the cladding back into the core. With single-mode fiber, it uses a laser-based transmitter, and it sends light directly through the core without any sort of reflection being used off of the cladding. Now, single mode fiber does have a smaller core compared to multi-mode fiber, and generally speaking, it's capable of traversing larger distances compared to multi-mode fiber. Now, to transmit between two devices, you need two cables, one for each direction. And this is similar to twisted pair that we were discussing before. You have a transmit port on one device, and that connects to a receive port on another device. And you can see that here on the SFP, where you have one for receive and one for transmit. And to use fiber, the device needs to have a built-in port that supports that connection type, or a modular port such as this SFP right here that allows you to use this method of Ethernet transport. If you have any questions about what was covered, please leave a comment below. And if you enjoy these tutorials and want to support my work, please like this video and share it with others. If you have the means, you can contribute to my Patreon or leave a tip in my jar. Be sure to subscribe to stay updated on my latest content, and thank you all for watching.